Hello everyone, let's solve some Leetcode today. So today we have 997 Leetcode problem, that is find the town judge. Now in this problem we have been given a very notorious and mysterious situation where there are n people labeled from 1 to n, and there is a rumor going on that one of these people is secretly a town judge. Now if the town judge exists, because it is still a rumor, we don't know whether it exists or not, but if they exist, then the town judge trusts nobody. Pretty similar to the normal judges, I believe, and everybody have undying trust in the town judge. And there is exactly one person that satisfies the properties 1 and 2. So what we are saying is that there can only be one and only one town judge if they exist. Otherwise, there will be zero town judges. So we will never have a situation where we can have two town judges or three town judges or four, because this property right here says that there can only be one person that is going to satisfy 1 and 2. So with these two, we can clearly say that the town judge is not going to trust anyone else, and everybody else is going to trust the town judge, which is a very crazy situation, right? Now here we have been given a trust array also. So in trust array, we have been representing the relationship for trust between two people. So trust array will have many of these kind of pairs where A and B are representing a relationship. So trust array will have many pairs like this. Here the A and B representing that A trust the B. It is a one-way relationship. Here we are just saying A trust the B. We are not saying that B also trusts the A. So this is actually just a one-way connection, just one way representation of a relationship. If we want to specify that B also trusts the A, we will have another pair with BI and AI. So here each of these pairs in the trust array represent a single way relationship. Now if a trust relationship does not exist in the trust array, then such a relationship does not exist. Well, clearly, right? I mean, if we have two people A and B, and A trusts the B, it does not necessarily mean that the B also trusts the A, right? So if we have a pair like A and B in the trust array, we can say that A trusts the B. But if we don't have a pair like B comma A in the trust array, we can definitely say that B does not trust the A, because this kind of relationship does not exist in the array itself. Now here the question is saying we have to return the town judge if they exist, otherwise we have to return -1. Simple. So if you really look at this problem properly, you will realize that it's a graph problem. Why? Because we have a trust array where we are defining the edges, which we are calling relationships in this case. So we can have multiple people A, B, C, D, right? And all of them will have some edges. So suppose we have a few people like 1, 2, 3, and then 4. So if I want to represent that 1 trust 3, I will have a pair like 1 comma 3, right? In the trust array. And it will simply mean that we have an edge from 1 to 3. Similarly, we can have 1 comma 2 also if 1 trusts the 2. Similarly, we can have 4 comma 1 if we want to represent that the 4 trusts the 1. And now here we are saying that we don't have this 3 comma 4. We don't have it because we are saying that 3 does not trust the 4. Simple as that. So you can see that it is actually becoming a graph. So here in this graph, you can see we have edges going all over the places. And now we have a few conditions for a node to be town judge. First one is that everyone trusts the town judge. And the second condition is that town judge does not trust anyone. So now let us try to look into the graph and understand what this truly means visually. So when we say that a node or a person actually trusts the another person, we know that there will be an edge outgoing from that node to the other node, just like we have in the case of C to B. So C trusts B, but B does not trust C, so we don't have this edge. We don't have the outgoing edge from B to C. And since everybody here in the village trusts the town judge, how many incoming edges will the town judge have? Well, we have n people, right? N people means n nodes, and we have to subtract 1. Why are we subtracting 1? Because we have to subtract the town judge, right? There will be no incoming edge from town judge to town judge in the graph. So it means that the town judge will have n-1 incoming edges, because there are n-1 nodes or people. And since town judge himself does not actually trust anyone, there will be zero outgoing edges. Just like we have an outgoing edge from D to E representing that D trust E, we are saying that the town judge will have no outgoing edge because he does not trust anyone. So it means that we have to find a node that have 0 outgoing edges and n-1 incoming edges, correct? So here in this graph, we can see that we have only one node that have 0 outgoing edges, that is A. And we have how many incoming edges? 1, 2, 3. But how many nodes do we have? We have 1, 2, 3, 4, 5, and 6. So we have 6 nodes that should actually have incoming edges into A, but we only have 3 incoming edges. So it means that in this graph, there is no town judge. No town judge exists. And so in this case, we don't actually have any town judge. So we will simply send back a negative one that we don't have a town judge. Now, in case we actually had edges from D to A, then we had edges from E also. Then we had edges from C also. Then now we will have 6 edges to A. And in that case, A have n minus 1 edges, 6 edges, and A have 0 outgoing edges. So we will simply return A. And that would be answer. So that is basically all we have to do. And we can keep track of the incoming and outgoing edges with the help of hash map. We will have 2 hash maps or dictionaries. One will be used for tracking the incoming edges and one will be used for tracking the outgoing edges from each and every node. So it means we will have a key for A in both of these dictionaries. One will track how many incoming edges are there for A. One will track how many outgoing edges are for their A. And at the end, we will go through all the nodes from 1 to n and we will check which node actually have n minus 1 incoming edges and 0 outgoing edges. Simple, right? So now let's go through the code. First of all, we are creating 2 dictionaries, in degree and out degree. In degree means the number of edges coming inside of a node. Out degree means the number of edges going out from the node. And then here we are taking the trust array and we are getting the A and B for each pair. And then we are checking if A is present in out degree or not. If it is not present, we will actually initialize the A with 0. Similarly for B, if B is not present in degree, we will initialize it with 0. Now the reason we are checking out degree for A and in degree for B is because we know that A trusts the B. So there will be an edge going out from A to B. So it means that A will have an outgoing edge. That's why we are checking out degree for A and B will have an incoming edge. That's why we are checking B in the in degree. And now if they are present, we will simply increment the in degree of B by 1 and out degree of A by 1. And we will do it for all the relationships present in the trust array. And after this for loop, we have data on all the incoming and outgoing edges from all the nodes in the graph. And here we are going through all the nodes in the graph. So we have n nodes as given. So we are going from 1 to n plus 1. We are going till n plus 1 because the range function is not inclusive of the upper bound. So it will not actually run till n plus 1. It will just stop at n. And here we are checking the count for in degree and out degree. In count will be 0 if I or the current node is not present in the in degree. Otherwise, we will check what is in the in degree and we will set that as in count. Similar for out count. The out count will be set as 0 if I is not present in the outer degree. Otherwise, we will take the count for I in the out degree and set it to out count. And then we will check the in count should be n minus 1 and the out count should be 0 for I to be a town judge. If this condition turns out to be true, we know that I is a town judge and we will simply return I because there can only be one single town judge. Otherwise, if this entire for loop runs and we have not found any town judge, then we know that there is no town judge, we will simply return -1. Now let us try to run this code and see what happens. So yes, our code is running in 27 milliseconds. We are passing all the 92 test cases also. So now let us take a look at the time and space complexity for this solution. So the time complexity for this solution is order of n. But then you will say, Satyam, it's not correct because we can have an edge from each node to every other node, which means everybody will trust each other and that will contain like n square edges in the trust array. N is the number of people and each person actually trusts the other person. So we will have n square relationships, which will mean we have n square elements inside the trust array. So why is it not n square? Why is it n? Well, let me tell you something, okay? So in computer science, we are talking about the input size. Now we have two things here in the question. We have people, number of people, and we have edges or the relationships. Now suppose that we had 4 people and 16 edges. 4 square equals 16. It means we have every node connected to every other node. But here also you will say it's order of n because you have been given an input size of 16 itself. What this means is that you are going to run a loop on the input size 16 and the loop will run this much time, the 16 times. So from your solutions perspective, you have only gone through each and every element inside of this given input only once, and that's why we are saying it is linear time complexity. It means that our time is increasing in proportion to the increasing input, but linearly, not quadratically, because we have 16 here as input, which we do not care whether it is square of the given number of people or not. We have been given an input of 16, so we will take that as input and then we will run a for loop on the 16. We don't care whether it is a square of 4 or not, because we are running a loop on the given input, not on something that we just created by ourselves inside of our solution. So yes, if we had an input something like 4 and we then actually converted that into something like 16 inside of our loop and 16 was not actually coming from outside, as an input, then we would say that, okay, you know what? We had this original input and then we converted this into the 16 and then we are running loop on this particular 16. Then we can say that, okay, we have an n square time complexity. But here 16 itself is part of the input. So in future, when we have 32 edges or maybe 64 edges or maybe 1 million edges, okay, we will still run the loop on each of these edges only once. So it means we still have an order of n or linear time complexity, because as the input is increasing, our time is also increasing, but it is increasing linearly. For 1 million input, we are going to run the for loop 1 million times. For 16 input, we will run it 16 times. We are not doing that, okay, we have the 16 input and we are running the loop 32 times. It is not like we have been given 16 as input and we are running some loop inside of our code for 16 square times. We are not doing that, right? We are only running it 16 times. That's why we are saying it's order of n. Simple. And the space complexity is also order of n, because we are just storing the in degree count and out degree count for each and every node inside of a dictionary. And the size of the dictionary will be, well, it will be equal to the number of people, right? Not the number of edges, of course. So ideally, I should have written 2.n or 2 multiplied by n, but it's a bigger notation, so we can actually remove this constant 2 and we just take the n. So yeah, like the video, subscribe the channel. If you have some kind of question that you would like me to target, or you have some kind of topic that you would like me to talk about, then just let me know in the comments. Now we will meet in the next video. Till then, bye.